There's this fascinating idea in the Big Bang Theory, a particular phase in the universe's evolution since the singularity, since the birth of everything that we see, called reionization. And I've been asked this by students upon studying the universe topic for Year 10 Science. It's called reionization. And to explain reionization, I need to first introduce the idea of something called an atom. So let me draw a simple atom. Okay, so this is a helium atom. So a helium atom has two protons, two positively charged particles, two neutrons, two neutral particles, so no charge, with two electrons, sort of like planets orbiting what's called the nucleus, the atomic nucleus. So where the protons and neutrons live, that's called the nucleus. So atoms are the basic building blocks of matter. Okay, matter is the stuff that we can see or can't see for that matter. So the air that we breathe, for example. So we're breathing in oxygen atoms every time we inhale. We're eating food, let's say that contains sugar. Glucose, let's say glucose is made of carbon, hydrogen, and oxygen atoms. And we're made of atoms as well. Billions and billions of atoms. So they make up the world that we see and the things that we can't see as well. So this is a helium atom. It's a very simple atom. It's the second most abundant element in the universe after hydrogen. And atoms, from everyday experience, atoms have a neutral charge. Neutral meaning that they're not charged at all. So hopefully when you're carrying a pen, let's say, or touching a table, you don't get zapped, okay? Because the atoms are neutral. Only when you do something like rub your feet on a carpet and then touch a doorknob and you experience a zap, that's due to charged atoms. I'm going to talk about it right now, actually. And that's due to the transfer of charge, in this case electrons, from the floor, carpet, to your shoes, to your feet, through to your body, and then through the doorknob. To give you some perspective on the size of atoms, so there's what's known as the fly in the cathedral analogy. So think of a fly in a cathedral. The fly represents the nucleus, the atomic nucleus, and the boundaries, the walls of the cathedral represent the electrons, the electron orbits. So atoms are pretty much more or less empty space, but with a very dense and tiny atomic nucleus at the center. Okay, they're 99.9% empty space. Okay. Now, most of the universe, it turns out, this is an interesting fact. I haven't really thought about this. Most of the universe is actually made of ionized atoms, charged atoms, not neutral atoms. So how does an ion form? So helium doesn't form ions from basic junior science chemistry because it's got a full outer shell. It doesn't want to get rid of any electrons or gain any electrons. It's happy like that. And the basic principles of chemistry, if you recall, only two electrons are allowed to fit in the first shell around the nucleus. So as you can see here, the maximum of two electrons means that the helium is happy. Let's however consider another atom. Let's consider hydrogen. Okay, suppose you've got a hydrogen atom here. Excuse my drawing. Now, hydrogen is the most simplest element in the universe. It's only got one proton and one electron. Now, hydrogen, in order to satisfy this full outer shell condition, atoms want to have full outer shells. Okay, they want to be stable. The hydrogen, it's best for it to lose its electron. Okay, when it loses its electron, you're left with what's called the proton. Left with the proton. And this is what we call here. This is what we call an ion, a hydrogen ion. Ion means charged atom. Okay, because we took the electron away now, we're left with an overall positive charge for the atom. Okay, so in this case here, in the case of neutral hydrogen, think of a seesaw. I always like to tell my students to think of a seesaw. It's good to picture this in your head. There's one proton, so one positive charge, and one electron, one negative charge. So the seesaw's balanced. Balance means the charges cancel out, and you're left with a neutral atom. Now, in the case of an ion, in this case, the seesaw isn't balanced. Okay, there's a positive charge overall, a net positive charge. Net means total. Now, sources of ions in the universe are pretty much abundant. So you've got things like the sun. You've got giant gas clouds, so big gas clouds between galaxies. Okay, you've got the regions around black holes. Okay, and so on and so forth. But these are pretty much common sources of ions, charged particles. Okay, other stars as well, apart from the sun, of course. The sun's a star. So let me explain this idea of reionization. So how the universe became, went through different phases from neutral to ionized, from ionized to neutral, back to ionized again. So I'll start with the Big Bang singularity. So the theory goes that around 13.8 billion years ago, everything that we see around us, the space, the time, the matter, and the energy, was once concentrated in this incredibly dense and tiny, this minuscule volume, okay, this singularity. This is where the laws of physics break down. Okay, now Einstein's theory breaks down, and any other theory, any other accepted theory that we know of in physics. There are possible alternatives out there, like string theory, which offer an alternative to explain this Big Bang, this singularity, what happens at a singularity. So at this point, all of space, time, matter, and energy was once contained. Even the idea of space becomes warped because, by definition, what's actually around the singularity? That's another question there. And the temperature of the universe, now, this is just an estimate. It differs from theories, maybe slightly, maybe by large amounts, but 10 to the 32, so it's 1 followed by 32 zeros, degrees Kelvin, capital K. Named after Lord Kelvin, renowned physicist. Physicists like to use Kelvin. It's an internationally recognized unit for temperature rather than Celsius or Fahrenheit. And okay, so around a millionth of a second, right? So in other words, 10 to the minus 6 seconds, a millionth of a second, a fraction, tiny fraction of a second after the singularity exploded. So this is called the Big Bang. That's where the word, that's where the phrase Big Bang Theory comes from. The singularity exploded, and around 10 to the minus 6 seconds after this explosion, you had what's called quarks condense out from this massive ball, this soup, if you wish, of stuff, this matter, this energy, all this sort of stuff that was once condensed. But it's widely accepted now that the singularity didn't really have any matter per se, as we're familiar with. The protons and neutrons was pretty much energy due to the extremely high temperatures and pressures, because at extremely high temperatures and pressures, the collisions between particles are so violent that you don't really get clumping of particles together. You've got just these particles whizzing around at extremely high energies and at high velocities. So 10 to the minus 6 seconds, at around 1 billion degrees Kelvin, actually. So 10 to the 9 degrees Kelvin. So 1 billion degrees Kelvin. So the universe was cool enough. I know it's an extremely high temperature, but it was cool enough for quarks to condense. And quarks are fundamental particles. Fundamental means nothing else is more basic than a quark, just like an electron. And quarks make up protons and neutrons. Okay, so there's a quark called the up quark, and there's a quark called the down quark. And these types of quarks make up protons and neutrons. There's other types of quarks too, like the top, bottom, and charm and strange. But for argument's sake, let's just focus on these two types of quarks. And also I'm putting in this into the mix as well. So I'm really simplifying this Big Bang Theory evolution, this timeline. Okay, so I'm clumping everything together as best I can. The quarks, 10 to the minus 6 seconds after the Big Bang, were formed, and we're able to form protons and neutrons. So protons are made of 2 up quarks. Okay, proton looks like this. If you've seen any of my previous videos, this makes sense. This arrangement of quarks, combination of quarks, makes sense because an up quark has a charge of plus 2/3, and a down quark has a charge of minus 1/3. Now, just some simple arithmetic. So 2 up quarks, if you add the charges of 2 up quarks, and you have a down quark with a charge of minus 1, we can get the net charge, the total charge of the proton. So 2/3 plus 2/3 is 4/3. 4/3 minus 1/3 is 3/3, and 3/3 is just 1. So a proton has a charge of plus 1. So that's where the charge of the proton comes from. It comes from its constituent particles, the quarks that it's made of. And then around 1 second after the Big Bang, after the singularity, protons and neutrons were able to combine into nuclei to form the first nuclei. The universe was cool enough to form the first nuclei. Okay, so you had things like hydrogen nuclei. So hydrogen, if you recall, has one proton. So that's the nucleus. A proton is called a hydrogen nucleus as well. You had helium nuclei, so 2 protons, 2 neutrons. And lithium as well, okay? So you had hydrogen, you had this sort of soup. The universe is still relatively warm from everyday experience, relative to everyday experience. You had hydrogen, you had helium, you had things like lithium, and electrons whizzing around as well at the time. So the very first, the earliest, the simplest elements, simplest atomic nuclei of hydrogen, helium. Let me rephrase this. The simplest of elements, the hydrogen, helium, and lithium that we know of on the periodic table, formed first in the early universe. And this phase in the universe's evolution is called nucleosynthesis. So nucleo concerns the nucleus. Synthesis means to combine, put together. So nucleosynthesis is the phase during which protons and neutrons could combine to form nuclei of the most basic elements. And around a quarter of the universe's mass comes from helium, lithium, and beryllium, interestingly. Now, the universe at the time couldn't make anything else because it cooled down so much that nothing else could sort of clump together. So then around 10 minutes after the Big Bang, you had this sort of seed, this sort of soup of protons, electrons, nuclei of helium, lithium, and beryllium. Okay. This is around 10 minutes. And the universe at this point was still too hot for electrons to latch onto nuclei. So you didn't have any atoms yet. So the universe was in this sort of plasma state, if you wish. And it actually took, amazingly, roughly 380,000 years after the Big Bang itself in order for the first atoms to form. The very first atoms, the most basic of atoms. So hydrogen was able to form, hydrogen atom, helium atom, lithium, and so on and so forth. 380,000 years. So it took quite a while, several hundreds of thousands of years for the first atoms to form. And you also had radiation just zipping about freely from the Big Bang itself. And about 100 million years after that, you had the first stars forming. Okay, and if you recall, stars, the basic constituents of stars are hydrogen and helium, right? So hydrogen in stars like the sun, basically nuclear reactors, they fuse hydrogen into helium. So first stars. And along with the first stars, you had things like black holes forming. And black holes, they contain what's called a singularity, just like the Big Bang. No one knows what happens to the singularity. Got this sort of ring around it. It's called an accretion disk. Okay, and the reason being is because the gravity at the singularity is so strong that not even light can escape from it. And there's a saying that once you go black, you can't go back. In other words, anything that gets sucked into a black hole, that's it. So as far as we know, it doesn't come out. So things like gas and dust in the vicinity of the singularity, sort of just like a whirlpool, they sort of start to circulate, sort of orbit really high speeds, and because of the high speeds of the particles in the accretion disk, lots of collisions occur. Temperatures go up and pressures as well, and so that's why black holes also give off high energy radiation. Okay, things like X-rays, gamma rays, and UV as well, ultraviolet light. So towards the high energy end of the electromagnetic spectrum. And so the first stars formed, you had black holes as well around. And at this point, if you go back to here, to the neutral atoms being formed, the neutral atoms that were lying around in like gas clouds then became ionized once again. Ionization, okay, about, during this time, so 100 million years after the Big Bang, the universe went into an ionized state once again because high energy from black holes, let's say from stars, would hit neutral atoms like hydrogen laying around, knocking the electrons away. And so then you get ionized atoms. And so this is called reionization. That's where the phrase reionization comes from. The universe went from a state of being ionized to neutral, then to ionized again. That's why it's called reionized. So really fascinating. And today we see these sort of hot coronas, these hot ionic clouds, if you wish, hot coronas, hot clouds of ions just floating around between galaxies and everywhere else in the universe. So a very fascinating idea in cosmology.